In this lecture, we will state some results about the tests of the diagonalizability of a linear operator. We start by a lemma that will be helpful to us in proving the theorem about the test of diagonalizability. So let's state the lemma. And this lemma states that let T be a linear operator. Let T be a linear operator, and let this lambda 1 to lambda k be the distinct eigenvalues of T, be the distinct eigenvalues of T, eigenvalues of the linear operator T for each I from 1 to k. For each I from 1 to k, let us choose a vector vi from the eigenspace of lambda I, E lambda I, which is the eigenspace corresponding to lambda I, corresponding to the eigenvalue lambda I. Now, if this v1 plus v2 plus vk is equal to 0, then vi is equal to 0 for all I. So what this lemma states? It states that if we have some k distinct eigenvalues of a linear operator T, and vi is chosen from the eigenspace of lambda I, then if the sum of these chosen vectors is equal to 0, then we have to show that each of these vectors has to be equal to 0. So here this vi is not actually necessarily an eigenvector. We are just choosing some element of E lambda I, the eigenspace corresponding to lambda I. Then if the sum of these vectors happens to be equal to 0, then actually each of these chosen vectors are identically equal to 0. So let's prove. We will state otherwise. We will assume otherwise. Assume to the contrary. Assume to the contrary that some vi's are not equal to 0. Suppose some vi's are not equal to 0. Then we will rearrange them. We will first list the set of vi's which are not equal to 0, and then we will list the set of those vj's which are equal to 0. So let u1 so on to ul be the list of vi's which are non-zero, and let ul plus 1 so on up to uk are equal to 0. So we are actually rearranging this list of vectors v1, v2, vk in a different order. And first we write those vi's which are non-zero, and then we write those vj's which are equal to 0. So let this u1, u2, ul, suppose there are l non-zero vectors in this list of k vectors, and the remaining k minus l vectors are equal to 0. So the first list of non-zero vectors is this u1, u2, ul, which are all non-zero, and let the remaining be ul plus 1 and uk, and they are all equal to 0. So actually we are just writing this u1 up to uk. It is the same list of v1, v2, vk, but possibly in a different order. So then as v1 plus v2 plus so on plus vk is equal to 0, we have u1 plus so on plus ul plus ul plus 1 plus so on plus uk. This is also equal to 0 because actually this list of vectors and this list of k vectors is the same list of k vectors, but now here this is maybe possible in a different order. But now since here we are assuming that ul plus 1 is identically equal to 0 and so on up to uk, they are identically equal to 0 and only the first L vectors are non-zero. So this gives u1 plus so on plus ul is equal to 0. And we are already assuming that each of these are not equal to 0. But then, now since u1, u2, so on, ul are the eigenvectors corresponding to some distinct eigenvalues corresponding to L distinct eigenvalues corresponding to some L distinct eigenvalues in the list lambda 1, lambda 2, lambda k. So here we are assuming this Vi is from eigenspace of lambda I. Now if this Vi is equal to 0, then it is not an eigenvector, but if some Vi is non-zero, then it is an eigenvector corresponding to lambda I. Now since we have rearranged these Vi's and have taken this u1, u2, ul as the set of non-zero Vi's, then this u1, u2, ul are some Vi's in this list. But since we are assuming that ui's are not equal to 0 from 1 to L, so therefore they must be the eigen. So they are the eigen vectors corresponding to some L different eigenvalues, because we have chosen v1 from eigenspace of lambda 1, v2 from the eigenspace of lambda 2, and since these are the k distinct eigenvalues, so this u1, u2, ul, they belong to k different eigenspaces. But since each of them are non-zero, so they are actually the eigenvectors corresponding to some L distinct eigenvalues. But we know that the eigenvectors corresponding to distinct eigenvalues are linearly independent. So, but since the eigenvectors, corresponding to distinct eigenvalues are linearly independent. Eigenvalues are linearly independent. Thus, if we have this combination equal to 0, thus u1 plus u2 plus so on plus ul equal to 0 is not possible. Because linear independence means that, now since they are the eigenvectors corresponding to distinct eigenvalues, so their linear independence means that each of their linear combination So each of their linear combination over the scalars from the field F means that each coefficient has to be equal to 0. But now here we see that the coefficients of these eigenvectors are equal to 1. So therefore this linear combination equal to 0 is not possible. So therefore we have a contradiction. So this is a contradiction. And so every vi is equal to 0.